Hello class, today we're going to be learning lesson 1-8 in your textbook, which is talking about how to represent functions as graphs. In the previous lesson we learned how to represent a function as a table or as a mapping diagram, and so that's what we're going to begin with. Let's start with just maybe a table. We know that the table had one column for the input, and we can label that just as the x, and one column for the output, which is the y. So let's just have an example. Let's say that I have 4 values for the input, which is the domain, 1, 2, 4, and 7. And let's say it was already plugged in and I was given that the range was 2, 3, 5, and 8. Well, all of this can actually be represented as coordinate points. So I can have the point 1, 2, the point 2, 3, the point 4, 5, and the point 7, 8, where I am labeling them in the correct order, x, y. And so I can plot all of these points on a graph. So let's do that. 1 going up 2, there's 1 point. 2 going up 3, 4 going up 5, and 7 going all the way up to 8. And I'm done. So this is really all that we're going to be learning in this lesson, is how to represent the data that we had before, which was given maybe as a table or maybe as just a list of the domain and the range, and now representing it in a graph form. Okay, by graphing those coordinate points. So let's start with a brand new one. This time I'm actually given the function y is equal to 2x minus 1. Okay, so I'm given the equation and I'm told the specific values that I'm going to plug in to this function for the domain. So let's go ahead and make ourselves a table where I have my x's and my y's. Okay, and I'm going to write down the 1, the 2, the 3, the 4, the 5 in the x column because that's my input, that's the domain. And let's plug it in. 2 times 1 is 2, minus 1 is 1. Let's do the next one. 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. 2 times 4 is 8, minus 1 is 7. And 2 times 5 is 10, and subtract 1, I have 9. And again, all of these can be easily represented as coordinate points. 1, 1, 2, 3, 3, 5, 4, 7, and 5, 9. So now just represent this function as a graph. All that I have to do is plot those points one more time. So my first point is 1, 1. The next one is 2, 3, so up 3. The next is 3 up 5. The next is 4 up 7. And the final one is 5 up 9. And I'm done. Okay, I don't need to connect those dots. All right, I'm just going to leave the dots as they are. Okay. The reason why I'm leaving the dots instead of connecting is because I only have a specific domain. For instance, I don't have 1.5 as one of my x's in the domain, which would kind of go about right there if I put a tiny dot there. But that's not one of the numbers that I plugged in. So I'm not going to put a dot there, and so I'm not going to connect the dots because it's none of those dots in between the dots that I did plot. Now, let's see if we can work backward. Sometimes you might be given a graph and asked, oh, based on this information, can you write a rule for this function? So that means, can you find what the equation would be that's represented by this graph? So all that we have to do is make ourselves a table, the x and the y's. Okay, and let's label them. So my first point was 1 all the way up to 2. The next one was 2 all the way up to 3. The next was 3 all the way up to 4. 4 up to 5. And 5 up to 6. Okay. So what we're trying to look for now is we're trying to look for a pattern between the x's and the y's. So how did this 1 change into 2? Did I multiply it by something? Did I add something? Well, I could have added 1 or I could have multiplied by 2. So let's check out these other ones to see which it could be. To make 2 into 3, it looks like I'm adding 1. And to turn 3 into 4, looks like I'm adding 1. And that same pattern seems to follow for each of my values. So that means that the function is going to be y is equal to whatever my beginning x value is plus 1. Okay. I'm also asked to identify the domain. So this means I'm going to list out all of the x values. So the domain was 1, 2, 3, 4, and 5. And then I'm also asked to list the range. The range is 2, 3, 4, 5, and 6. And I'm done. This right here would be everything that I was asked to answer. Okay. Now, there's something else that I wanted to show you. And this is how you can determine, just by looking at a graph, if it is a function. You might be asked that sometime. So let's go ahead and just graph some points. We're going to graph some points that look like they're in a V shape. Okay. The rule that I want to show you is called the vertical line test. And what this means is that if I can draw a vertical line anywhere on my graph, okay, I'm going to just draw some random vertical lines, never will it pass through more than one point. And if it passes this test, then it is a function. Okay, I could not find a single place on this graph where one of my vertical lines passed through 2 points, or even more than 2. So the vertical line test is really important. It can only pass through 1 point. And that's really all that you need to remember. Okay. Let's draw another one. How about we draw another V, but this time it's going to be sideways. So it'll kind of look like a less than symbol. Okay. I'm going to pick a point and I'm going to draw a vertical line. Well, right there it looks like it only passes through 1 point, but let's just draw a line somewhere else. Oh, it failed because it passed through a point right up here and down below. So this would not be a function. It failed the vertical line test. And the reason is because of what we learned in our last lesson, that any input, like if I plug in the number 4, I should only get one output. So I should only get, in this case, the number 3. But it said, oh, also if you plug in the number 4, you get the number 7. And that can never happen. You cannot get 2 outputs for the same input. Let's just do one more. This time we're going to make a function that kind of looks like it's in a parabola shape, which is something that you'll learn later on. Okay. Again, it doesn't look like it's forming any straight lines, which is what you've seen before. These are very straight lines. This line is kind of more curved if I were actually going to connect the dots. But I could see that any vertical line that I draw through this function will only pass through 1 point. So this as well is a function. Okay, so remember the vertical line test. It's really going to help you out in the future. So to kind of close, I just wanted to organize all of our thoughts from the last 2 lessons now of ways that we can represent a function. Okay, so sometimes a verbal phrase is going to be given that's going to represent a function. So maybe it'll say the output, this is just an example, is 1 less than twice the input. Okay, so maybe you see this in a word problem and it's written out as a verbal phrase. Okay, if I was going to translate that into an equation, then I would say the output, so the y, is equal to 1 less than twice the input. So the input is x, so twice the input would be 2x, and 1 less than that would be subtracting 1. Okay, this could be represented in a table if I chose some values, let's say 1, 2, 3, and 4, and I plug those values into my equation, then I would get 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. And 2 times 4 is 8, minus 1 is 7. So the final way that I could represent a function would be by graphing the input and the output as coordinate points. So 1, 1, 2, 3, 3, 5, and 4, 7. And I'm done. So we've learned all these different ways now to represent a function. So on your own, before you come back to class tomorrow, I want you to try to graph this function right here. Y is equal to 2x minus 3. So what you need to do is you need to make yourself a table, and you're given a very specific domain. So plug the domain in, turn those values into coordinate points, and just simply graph it on a grid like I have here. So any questions that you have, come to class with when I see you tomorrow.